pictures of arctan. Well, how can I label the size of this triangle so that the tan of this angle is x? So I just go like x and 1. That is a picture of arctan x, the angle whose tangent is x. And Pythagorean theorem tells me that this is root x squared plus 1. And now I can just compute, all right, well, what is cosine y then? Cosine y is, reading off my picture, 1 over root x squared plus 1. So what is cosine squared y? It's just 1 over x squared plus 1. Okay? On the other hand, if x is negative, I have to be a little bit more careful in how I draw my picture. How can I label the size of this triangle in such a way that the cosine, or that the tan of that angle is x? Well, I can still do x and 1, and now since x is negative, that number is negative, so I'm going down, so everything's cool. So this is root x squared plus 1 again, and I insist that you make the picture both ways. Sometimes it turns out to be relevant and sometimes not. In this case, what's the cosine of y? It's 1 over root x squared plus 1. Still, by the way, you can double check these for accuracy. Since this is the first quadrant angle, should its cosine be positive? Yes, that's a positive expression, and the cosine should be positive in the first quadrant. That is also a positive expression. Should the cosine of its fourth quadrant angle be positive? Yes, since cosine is the x coordinate. So if that's that, then that's cosine squared y is 1 over x squared plus 1. All right, so all of this giant thing here in this box was really for us to conclude that cosine squared arctan x is 1 over x squared plus 1 in both cases. Whoa! So dy dx is 1 over x squared plus 1. Damn. This is kind of amazing. This should just blow your mind. I know that I say that every single class, so maybe you're feeling like fatigued, but pit pause, take a nap, and come back if you need to. This is an amazing fact that the derivative of this inverse trig function is in fact an algebraic function, a simple rational function. Somehow, though tan is like defined in terms of angles and sines and cosines, the derivative of the arctan is growing at a rate which can be described algebraically with simple, simple rational function. I think that's incredible. All right, let's now check to see if this was a good guess that we made. And the answer is, yeah, it was. Because, like, that's 1. And in order to, if I want to graph 1 over x squared plus 1, then I can just graph x squared plus 1, which looks like that. And then use your skills in graphing reciprocals of functions. The reciprocal of that function will be small when this is big. And then like this. All right, amazing, amazing. Yeah, and if you are worried that maybe your initial graph you thought that it was pointy here, it's not pointy. All right, and there are particular students who got all up in my face last semester about this. You know who you are. You now have the skills to prove that the 1 over x squared plus 1 function is not pointy. Differentiate 1 over x squared plus 1, and you will find that it is indeed has a derivative of 0 at 0. So, all right, our guess is perfect. Everything is beautiful. There's about one more thing I want to do on this subject. It just occurred to me. I don't usually do this, so you can kind of ignore the next 2 minutes if you want. But it is possible, let's see, let me erase this. It is possible to do this a little bit differently, analogously to how we did the, well, just watch. An alternative derivation of this. Okay, I'm not really prepared, so let's see if, I might screw this up. But if what I want to do is to differentiate arctan x. Like I said, not totally sure what I'm doing. But I think what I could do is I could differentiate no, here's what I do. Let's try to come up with the derivative of the tan of the arctan of x. Oh yeah, here we go. All right. Well, what is the derivative of what is the tan of the arctan of something? The tan of the arctan of that something is, by the definition of arctan, just x. And the derivative of x is 1. Okay. Well, what is the derivative of the tan of something? By the chain rule, the derivative of the tan of something is secant squared something. Back inside for the derivative of the something. Whatever that is. Okay, so putting this all together, what we really have is that 1 is secant squared arctan x times the derivative of the arctan, whatever that is, and thus the derivative of the arctan function is cosine squared arctan x. And by our pre-calculus, that's 1 over x squared plus 1. Again, this method, which I'll just call like method 2 or something, is the exact same thing as method 1. It's a little bit more abstract. There's a little bit less writing. Some of you might find it simpler. Some of you might not. This method is just that method by introducing an extra variable to just keep things a little bit simpler. But over here, yeah, if you just analyze these two methods, you'll see that they're really just the exact same thing. Okay, 1 down, 5 to go. If you turn to page 2 of your packet, you have the derivative of arc cotan. Well, that turns out to be very, very similar to the derivative of arctan. So you are going to do that yourself later. Let's do the derivative of arc sine right now. So while I'm erasing the board, please turn to page 3, graph sine, restrict its domain, graph arc sine, guess what you think the derivative of arc sine should be, then do the algebra, and I'm going to tape all of this, and that'll bring us to the end of this, me talking in the room by myself, and then we will have Wednesday's 9th period class, which will also get taped. And then on the Thursday snow day, you can all sit around and learn a bunch of calculus. Cool. And then I gotta quickly get out of this room before this teacher knows I was ever here. All right. And those of you on the internet, you should download this packet off the website and do this. They're nice, pretty graphs. Teaching alone in a room. It's so weird. All right, that's sine. This function is not one-to-one, so prior to constructing the inverse function, I must choose a particular interval such that the function then will be one-to-one. I choose the interval from negative pi over 2 to pi over 2. Thus, when I go to make the arcsine x graph, at pi over 2 it's 1, so at 1 it's pi over 2. At negative pi over 2 is negative 1, so I have a point negative 1, negative pi over 2. At 0 we have 0. And then the curvature is going to be like opposite. So it's going to be like, alright, that is how you rederive everything there is to know about the arcsine function. It looks like that. I feel like we're good to go. Okay, so here, over here, please guess what you think the derivative of this function should be by just making a sketch. Make a sketch over here. Well, pause if you need to finish it on your own. But if you start thinking about this, well, like what's my slope here at like negative 1? Well, that is like matches up with like the top of that sine curve. So it's the derivative is 0 here. The derivative is like infinite here. So the derivative is like an infinitely huge number, and then I'm a tiny bit more than negative 1. It's still like a huge positive number. It's a huge positive number, huge positive number. What do we think the slope of that line is? Okay, well, this line, even though it doesn't totally look like it on my graph, the line which is, as we know, the line which is tangent to the sine curve at 0 has slope 1, thus the slope of this line is also 1. So we have the slope of this being a huge positive number, then the slope being as small as 1, but now the slope starts getting bigger again. So now the slope becomes huge, and it goes up to infinity again. All right, so if you're kind of a pro at this, that tells me that the derivative function should probably look something like this. It should be a huge positive number, becoming a smaller positive number, then eventually getting as small as 1, and then going back up again. So I don't really know any function that looks like that. It kind of looks like secant or something, but it's between negative 1 and 1 instead of between negative pi over 2 and pi over 2. So I really don't know anything about that. All right, now this process should look extremely familiar, this process we're about to do, because it's the exact same thing we just did with tan, so I'll go a little bit faster. How can I differentiate y equals arcsine x? Well, rewrite this equation as a sine equation. If y equals arcsine x, then that means that the sine of y has to be x. You should definitely like do this whole thing yourself, because it really only takes like 5 or 6 minutes, and then watch me do it. Don't just watch me without trying it first. All right, now I differentiate both sides with respect to x. The derivative of sine y, well, the derivative of sine of something is cosine something, back inside for the derivative of the something. And the derivative of x is just 1. So what is dy dx? Dy dx is just 1 over cosine, or just secant y. Alright, so that was actually even easier than the arctan formula. Now what I have to do is some precalc. So do some precalc. What I need to know is, this is really like saying, what is the secant of the arcsine of x? Okay. Well, there are 2 cases to consider. If x is a positive number, then the arc sine of it will be between 0 and pi over 2 in quadrant 1. If x is a negative number, then arc sine will be between negative pi over 2 and 0 in the fourth quadrant. So again, we consider the x is negative case and the x is positive case separately. If x is positive, we are in quadrant 1. If x is negative, we are in quadrant 2. So I draw my little rotational angle arrow, and now I have to label the sides of the triangle in such a way that the, what am I trying to do? Oh, I'm trying to make a picture of, arc sine. Picture of y equals arc sine x. So what is the sine of y, or what is, I'm trying to label the sides of the triangle in such a way that the sine of this angle is x, so I just do x1, boom. The sine of that angle is now that. So then this becomes 1 minus x squared. Okay, let's do it. What is the cosine of y then? Cosine of y is boom over boom. So secant y is 1 over root 1 minus x squared. Does that make sense? Is this a positive quantity? Yes. Should the cosine of a quantity be, should the cosine of a first quadrangle be positive? Yes. So this is looking good. How about over here, to be a little careful, how do I label the sides of this triangle in such a way that the sine of that angle is x? Well, again, I think I can just do x and 1. Since now x is a negative number, it makes sense that it would be going down. And then this becomes root 1 minus x squared again by the Pythagorean theorem. All right, what is secant y in this case? We can just know that secant is the ratio between the hypotenuse and the adjacent. So I really just get 1 over root 1 minus x squared. That is a positive quantity. Should we expect the secant of something positive? Should we expect the secant of a fourth quadrangle to be positive? Yes. Okay, so it turns out again that it appears as if I have wasted my time. What I've learned from this pre-calculus activity is that the secant of the arc sine of x is just 1 over root 1 minus x squared. So, turns out that that is the derivative of arc sine. Again, it is an algebraic function. It's not a rational function at this point, but it's like, you know, reciprocal of a thingy. All right, last step is to check to see if this formula seems reasonable based on our guess. So what we now have to do is graph, just imagine this were pre-calc A or whatever, and someone just walked up to you out of the blue and said, yo, graph y equals 1 over root 1 minus x squared. How would you do that? Looks hard. Well, it's a reciprocal of something. So if I can graph root 1 minus x squared, then I should be able to graph its reciprocal. Do you recognize root 1 minus x squared? You should. It is a semicircle. Root 1 minus x squared is a semicircle of radius 1. So if we kind of draw that in first, and now reciprocate that function. So when you reciprocate that, you're going to get this thing, which like 1 over a tiny positive is a huge positive. 1 over 1 is 1. And we're going to get this. So again, it seems like we guessed correctly by just sketching it and then seeing what we got when we did the algebra. All right, 2 down now out of 4. Page 4 is the derivative of arc cosine, which turns out to be very similar to the derivative of arc sine. And then page 5 and 6 are hard. Those are the hardest too. You're going to do those on your own, and you're going to come back knowing, you're going to come back next week knowing all the formulas for the 6 inverse trig functions and doing a whole bunch of homework on all of this stuff. That is lecture 13. That's not actually lecture 13 because I am now leaving this room, walking back upstairs, and I'm going to take over, and you're going to watch what period 9 is doing on Wednesday. All right, good. Bye, class. See you in a few minutes.